Today, I'll tell you something about logic and proofs in cyber-physical systems. Tomorrow, I'll zoom into the differential equations part. So if you're here for the talk tomorrow, which is at 10 o'clock?
10 o'clock.
I'll tell you a lot more details about differential equations, but today I want to give you more of an intuition, more of an overview, more of what does the reasoning look like in principle that we're doing, and what on earth is it good for, applications and so on. So, first of all, there's the cyber-physical systems analysis question by way of the aircraft example. So if you're the pilot of this aircraft and there's other aircraft nearby, what are you going to do? And if you're the person responsible for designing the computer control system for this aircraft, how are you making sure that every advice you give the pilot is a good one? Because there's no time to sit down and plan all the trajectories out. You need to know right now that a strong right turn is the right thing to do. And that's just by way of example. Cyber-physical systems are more general, anything that mixes computation with physics to solve problems that none of the parts could solve alone. And of course, once you think about it, CPSs are everywhere with a lot of prospects for improved safety and efficiency. Driverless cars, for example, self-driving cars, driver safety assistance technology, UAVs, trains, robots. This is a very biased sampling of the systems that I had my hand in. They show up everywhere else as well, these CPSs, but the prereq in all of those cases is, of course, that they need to be safe. Otherwise, you're not actually making the world a better place.
And when you mentioned aircrafts, do you assume that you know what the other plane is doing, or you just know?
That's part of the challenge, right? And all of these is part of the challenge. You need to assume something about the others, but you can't assume perfect knowledge about everything else as well, because a lot of the challenges come from, even subtle misunderstandings, right? So, for example, let's stick with the aircraft example. It sounds like a brilliant idea to say, it's easy. Whichever aircraft is higher up will keep on climbing. The other one should descend. Great idea, won't work, because if both of them believe there's currently higher up and they have slight measurement errors, they'll both fly up and collide. So that's where a lot of the challenges come from in systems, uncertainty, right? As Niels Bohr said, right, you can't say it any better than he did, like predictions are hard, especially those about the future, right? And here you try to predict the future of systems all the time in some safe sense, right? So the question somehow is, can you trust a computer to control physics? And the answer depends. It depends on how the system has been programmed and what will happen if it malfunctions. So for example, the Bluetooth controlled GPS guided electric toothbrush does very limited damage, but the same isn't true for the aircraft that got me here, for example. So the rationale behind my research is that of course we could trust computers to do good things in cyber-physical systems if only they came with guarantees. And you do need a lot of mathematical foundations in order to get such safety guarantees. You do want a common foundation for these systems. You do not need special math that only works for trains but doesn't tell you how to drive a car, for example, but you want the same kind of mathematics. Of course, the answer will be very different in each of the cases. You can't conclude from being able to ride a bike that you know how to fly a plane. There's a few steps in between, but it shouldn't be different kinds of mathematics that you use to come up with the answer or to justify why the control is not safe. Of course, foundations have revolutionized the digital part of computer science and indirectly our society, but we need much stronger foundations when that software starts reaching out into the physical world. So my conclusion, which I hope is a welcome one for you, is that cyber-physical systems do deserve nothing less than proofs as safety evidence, which is precisely why I'm worrying about that. And my secret weapon is to understand cyber-physical systems as multi-dynamical systems, by which I mean systems that feature multiple facets of dynamical systems. Part of them is a discrete dynamical system, coming from the discrete control decisions that happen over time in a computer. I take a step of computation, I decide something, I take another step of computation, I decide something, or maybe I communicate. Other parts of that are very visibly of continuous dynamical systems nature, the very motion of the aircraft through the air on the second slide, for example. But other dynamical systems features might happen as well, for example, adversarial dynamics, whenever you have uncertainty that is resolved against your best interest. You have non-determinism whenever you have uncertainty that's resolved in any arbitrary way, or you might have stochastic dynamical systems effects whenever you have like quantitative probabilistic information about things. But the point is that if you just describe a system as being composed out of these different dynamical systems, you have made the description of the system a lot easier, because at least you identified, there's just this discrete part, and there's this other continuous part, and then there's this adversarial dynamical part. So each of the pieces, by definition, is not as complicated as the original system. So all that you need to make sure is to carry this descriptive simplification over into an analytic simplification, and you've basically won. So what you need to make sure is that if the system is defined as a composition of simpler things, if you make sure that your analysis works as a function of an analysis of the pieces, you can work on analyzing even rather complicated systems. And that's precisely where logic comes in, because logic does have a compositional meaning. The meaning of A and B, well, that's the set of all states in which A is true, intersected with the set of all states in which B is true. Moreover, our analysis for an AND formula will also be compositional. A proof of A and B consists of a proof of A together with a proof of B. All we need to do is make exactly the same principle happen just for the operators of cyber-physical systems and not just for AND. Let's jump right in and make that happen. Before we do, hybrid systems is the class I will be focusing on the most. It's the intersection of discrete continuous, but keep in mind what I say generalizes to hybrid games, adversarial dynamics mixed in, stochastic hybrid systems. There are also others that aren't even in this picture, distributed hybrid systems, the things that happen if you have, for example, lots of cars on the road or lots of UAVs flying in the air. Each of them has their own personal logic. Differential dynamic logic is what I will be focusing on today for hybrid systems, but there's, for example, differential game logic for games and so on. Good. Here's my favorite cyber-physical system, the Wally robot, which moves in a corridor environment and is trying very hard not to bump into obstacles. And of course, part of the behavior of Wally will be discrete. For example, steering decisions or speed up, slow down decisions. Other things will be continuous of nature. For example, the change of velocity or position over time. So logicians have invented the box operator to say all of Wally's behavior such that Wally's position is not the obstacle's position, which means no matter which state we go to, Wally's position isn't the obstacle's position. But the question is, what does the always mean in this? And that's where the basic idea comes in, that you need to pick up Wally and squeeze him inside the logical always operator to say all of Wally's motion is such that Wally's position is not the obstacle's position. In that particular, all the transitions are those that the Wally robot can do. But even the best and strongest logician can't physically pick up a Wally robot and squeeze that one inside the logical formula, but you need to develop a model of what Wally robot is capable of. Let's do that. Part of the model will be some ordinary differential equation describing the Wally robot motion. This is obvious straight line accelerated motion, the simplest one that fits on the slide. But other parts are more of a discrete nature. For example, the decision to change the acceleration to a -1 for braking, which isn't always a great idea, so there's a bit of a programming language around it. For example, to say that only if some start braking condition is true for Wally's position and the obstacle's position will we change the acceleration to -3, and maybe otherwise we'll speed up, for example, and the two need to meet. So they meet here in sequential composition way. That means first you run the discrete controller. Having done that, you run the differential equation for some arbitrary non-deterministic amount of time. If you've done that, you've had one control decision, which is a bit not enough for a robot. That's where the repetition operator comes in, which says, oh, and now you get to repeat this any number of times. To say, first do the control thing discretely, then follow the ODE for any period of time. Then you get to repeat if you want to. So again, change control decision, follow ODE, change control decision, follow ODE, and so on. Does the dynamic systems model make sense to you? This is how discrete and continuous meet, and likewise in ways with the adversarial dynamics meet. Good, but remember where we came from. We were just developing this Wally model in order to have something to squeeze inside the box operator and staple the post condition behind, which now says all of this particular specific Wally model is such that all of its behavior will make sure that Wally's position is not the obstacle's position. And now that I've said this, I have alluded to what its semantics is, and I can ask you whether this formula is a true or false one. And you can tell me which one it is. Does this look like a true formula, or does this look like a false formula? Any opinions on it?
Depends where you start.
Precisely. So it has to look like a false formula to you, because if you start in a collision state, nobody's going to tell me that you always stay collision free. It just can't be true. But logic is very good at managing these assumptions. So you just need an implication in which you say, well, first of all, I guess my position shouldn't already have collided, and maybe my brakes should work, and some other stuff. They now imply that all of this behavior is safe. And of course, whether it is still depends on what. Did I set that breaking point correctly? And that's, of course, already highlighting one of the design challenges in these systems. It's not so hard to write down the schema of a system, writing down what roughly it is capable of. What is much harder is figuring out what are the control conditions. So when exactly should I do what? Question.
Yes, so I just have a concern about Wally.
Poor Wally.
Can happen that like the time that the robot will do blue thing, evolve it differential equation will be too large,
Precisely.
so that the control won't be run.
Precisely. 10 years from this is probably a bad idea, because it is never safe to accelerate if you might be stuck with this decision for the next 10 years. Well, maybe except with your spaceship or so. Right? Yes, so in other words, you will have to limit the continuous motion a little bit too much, because unrestricted differential equation is usually too strong of a model for hybrid systems. But the way you do this is you staple a domain to the differential equation in which you either say run while the velocity is at most 20, or you say staple an evolution domain constraint to the differential equation that says run, but maybe at most for half a second, because then I want the discrete controller to act again. But having said that, there are a few systems where you get away with this unrestricted motion. Not Wally, in fact, but it just didn't fit on the slide anymore, so I had to do it. Yeah. So here's the language a little bit more formally motivated by this example. There's a program, a hybrid program language, and a differential dynamic logic language. First, the programs. Putting new values into variables by discrete assignments gives you the primitive for discrete dynamics. Testing whether logical formulas Q are presently true gives you a way of checking conditions on the current state. The idea is that if the formula Q is true at the moment, yeah, nothing actually changed. You're still the same person. Your state didn't change, but at least you passed the test. Think of this as a test in a class, right? If somebody gives a test in a class, you need to pass it, and then you're still the same person, but at least you continue to be enrolled in the course. You are not forced to drop. And it's the same thing here as well. Differential equations gives you the primitive for continuous dynamical systems, where again you see these evolution domain constraints that you put out as a necessity. You can write down logical formulas attached to this. Think of these as real arithmetic formulas, but it's not that important what it really is. Anything like this would work as well. That tells you follow this ODE for any non-deterministic period of time, but never ever dare to leave Q. Then non-deterministic choices between a hybrid program alpha or beta recursively built out of this way. This would now correspond to a robot that can either accelerate or brake, or steer left or steer right. Or think of a car in front of you, it might slow down or not, who knows, right? Sequential composition means first run, let's say, the discrete control and then the continuous, or first speed up and then slow down. And here's the repetition operator that says, repeat the alpha control loop any number of times. Non-determinism is important in all of those circumstances, because you're trying to describe a model of reality. And if you're too specific with your description of that, it will be the wrong description. Out of these operators, you can define everything else. For example, ordinary if analysis are just a choice where on the left-hand side you start with a then condition, and on the right-hand side you start with an else condition. But in these hybrids, or in these models of reality, it's often better to have them overlap a little bit, because you want to express flexibility. And your controllers aren't never going to do exactly what you told them to. Good. That was the programmed language. And then the formula language is just real arithmetic, so real closed field arithmetic with quantifiers of the reals. And most importantly, for any hybrid program alpha and any differential dynamic logic formula P built recursively like so, This is again a formula that means all runs of the hybrid program alpha satisfy P. And this is the dual that says there is a way of running the program alpha to a state where P holds true. Any questions about the language before I go on? Cool. Well, writing down the language and writing down a formal of semantics, which I haven't shown you, but I think I explained to you well enough how this works. It's a very simple systems principle. Is one thing, but being able to reason about them is much more useful. And here are the axioms that we have for our reasoning, which you should think of as equations of truth. For example, this one says all behavior of a system that has a choice to do alpha or beta, we want that to be safe. Well, that's the case if and only if all alpha behavior is safe, and independently all beta behavior is safe. Oops. This one, for example, says all behavior of a system that first does alpha and then does beta is safe. Well, that's the case if and only if it is true that after all of alpha behavior, this more complicated postcondition is true. And the more complicated postcondition says that all beta behavior is safe. In other words, first running alpha, then beta, we're safe, if and only if it is true that always after running alpha, it is true that always after running beta, we're safe. Very innocent reasoning axiom, but super powerful, because all that happens syntactically, which makes it so easy for me to teach my computer how to do that, is that you basically need to find the semicolon and turn it and split the box. Right? That's very easy to do. Assignment, for example, right? After assigning the value e into x, p is true of x if and only if p is true of the value e that x is going to get in any second. So it's very easy to do these things. The harder one is differential equations, right? And of course also the most interesting one in a certain sense. A property p is always true after an ODE if and only if it is true for all times, that if I plug the time t into the solution of x, I hope I get that, and discretely jump instead, then if p is true afterwards, that of course precisely means that the property p was true all along the ODE. Yeah, but of course this axiom is only okay to be used if we happen to find such a solution x. That solution has to be a solution of the symbolic initial value problem, because we usually don't know the numerical initial value either. And so in other words, that is correct, but super naive. It basically works only on the boring ODEs. So later on a little bit, and tomorrow for real, I'll tell you what we do in interesting differential equations instead. But certainly if you happen to have a solution, you should be allowed to use it. What's actually interesting and slightly surprising is that you have a soundness and completeness theorem here, which means that properties of hybrid systems, if they're true, they deserve a proof. If they're not true, you shouldn't have a proof of it, because that would violate the soundness of our reasoning. And yes, all of the axioms I've shown you are sound. But the converse question also is a very interesting one. The question, if it is true, is there a proof of it? The world will go on if the answer to this question is no, but it kind of would be cute. Right? It happens to be true in the following sense, that if a formula is sound and complete relative to either differential equations or to discrete dynamics, that means, of course, reasoning about hybrid systems is hard, because reasoning about reality is kind of hard. And if you don't understand the differential equation, you can't understand the hybrid system around it, because it's part of it, right? If you can't understand the discrete system, you can't understand the hybrid system which is around it, right? But shockingly, it turns out that if only you understand the differential equation, you already understand the hybrid system, because it is actually complete. Hybrid systems proving is complete relative to continuous systems proving. That means every true property of a hybrid system can be proved from elementary facts of differential equations, and moreover, the proof of this completeness theorem is a constructive theorem, so you can follow the recipe. And it will highlight what are the questions about differential equations that you need to answer in order to have answered the safety of your hybrid system at the beginning. Now you can say, maybe that means differential equations are the actual hard question in the hybrid systems analysis. That may be true, but the second completeness theorem is also correct. The one that tells you, and vice versa. Which means every question about a hybrid system can be reduced to a question about a discrete system. In particular, actually, Every question about a continuous differential equation can be reduced to a purely discrete question in an infinitely if way. And vice versa. Every true question about a discrete system can be reduced to a differential equations question. More interestingly, every question about a hybrid system can be reduced to either the continuous or the discrete side, however way you see fit. And the most successful way of making sense of the two completeness theorems is that also implies that every hybrid systems question can be reduced to some mix of discrete and continuous questions for which this happens to be most natural. If a particular question is very naturally phrased and answered as a continuous one, please go ahead and do that. Don't start discretizing it. And if another part of the system is most naturally phrased discretely, go ahead and answer it discretely. And this is sort of the guarantee that the two sides will be able to match back together into the proof, if it was true in the beginning. Okay, but that means sort of also flip side, I guess we kind of need to understand better how to prove properties of differential equations, because if everything somehow boils down to that, maybe we should have a better way of answering that. And certainly, just working from solutions sounds like the entirely wrong way to do it. So, let's zoom in a little bit at least into this, and I'll show you a few examples as well. One way of proving if this is the vector field of a differential equation and this is the solution of the differential equation, that you never enter the bad blue region is start the system at each and every one of those states, compute a solution. These, of course, will be infinitely many computer solution questions. Then check at every point in time whether you're in the bad blue region or not. If you have infinite amount of patience, this is a great approach. I don't. So instead, the way we do this is basically work from directional derivative, with the intuition being, if I find a point where my dynamics pushes me from safe into unsafe, I guess my system is in trouble. And if I never do, then the intuition is that if I start somewhere safe, I'm going to stay somewhere safe. I don't know where exactly, but that was never actually the question. Does the intuition make sense to you? Great. These are invariants for differential equations. Differential cuts is a logic principle generalized to ODEs, where basically, if we have a proof that we cannot enter the red region, then I can cut the red region out of the state space without loss. Having done so, if I then find a proof that I also cannot enter the other red region, now that I know I can't go down there, it turns out I also can never go up there, I can cut this out of the state space as well. Then I look at my state space and say, no wonder the system is safe because I ran out of bad blue regions. This is changing the dynamics of the system, the differential cut. Usually this is very dangerous to do, because usually it's a bad idea to say, I want you to analyze this system, and you come back with an analysis of that system. I'm not sure that's good for me. But the point is, if you first prove that you can't get into the red region, that's okay. Think of it this way. If somebody hands you a robot, and you don't know what the robot does, but the first thing you do is prove that it can't fly. From that point onwards, you can reduce the analysis to the 2D surface of the Earth. Having done that, you next find out that your robot is unable to leave the road. Now you can reduce your analysis to what does it do on the road. Having done so, you can maybe next prove that it isn't leaving the lane. And then you can reduce your analysis of the robot to the question, does it happen to bump into the car immediately in front of it or not? And if the answer is also no, then over time you've gathered enough knowledge about the robot to say, I guess it's safe to be turned on. Good. Differential ghosts are another crazy proof thing. Sometimes what happens is that the analysis of one differential equation isn't working out very well. You can solve that by making the world more complicated and adding a differential equation to it, which sounds like a totally stupid idea, because which fool would reduce the analysis of a 10-dimensional system to an 11-dimensional system? But it turns out that can sometimes be a great idea. In fact, I'll show you tomorrow how much of a great idea this is. The point is, sometimes you can do this in a clever way by dreaming up this extra ODE such that you generate a new invariant that wasn't there before. Think of this as the proof theoretical analog of dark matter. In physics, you look at the world, say, that's crazy, my energy invariants don't balance out. There must be something I can't observe. This thing, I will hypothesize and make it up, and I just call it dark matter, and will write the differential equation down as I see fit. And later on step back and say, this generalized energy invariant that I now made possible is actually balancing out. And it's kind of the same idea also for differential equations proof. And it's shockingly powerful. How powerful, I'll tell you tomorrow. And in fact, the point is, you can prove every true real arithmetic invariant about differential equations that way around. And you can decide them just by doing this a bunch, right? But you need all of them, but the most fascinating one and the one that you need the most is the differential ghost thing, like making the question harder by adding on dimensions. Good. But pictures are not as useful as proof rules. So here's a proof rule rendition of this differential invariant principle. So it means that if I assume that I start in P and I want to show that I always stay in P while following a differential equation within the evolution domain constraint Q, then it is enough to prove that my evolution domain constraint implies P prime, so a differential of P. It's actually literally defined as a differential form, but I'll show you in a few slides an example what it really does, where you leave around the discrete shadow of the differential equation. So you basically select the vector field for it by assigning the right-hand side of a differential equation to the left-hand side of a differential equation, which is now a discrete variable, and this is just a jump, as opposed to a continuous time evolution. I think this will be very clear in slides, but the point is, basically, if you can prove it by deriving it, you're done. Differential cut is this principle that if you have an invariant question and about an ODE, it could also be a different question, but for the slides I made it just for invariant questions. If you prove that you never leave the region C, then you can assume C is part of the evolution domain constraint from now on. If you've seen Gerhard-Genson's cut principle in logic, that's precisely what it is just for differential equations. In Gerhard-Genson's cut principle, you first prove a lemma C and then use the lemma C from now on. Here you do the same thing, but for a differential equation, which means you first prove about the ODE that you can't leave C, and then you will make a pseudo restriction of the dynamics to be edited to be by assumption, never leaving C from now on. That's okay, you just proved you can't. And then these differential ghost guys, where you prove that if you dream up an extra differential equation y prime equals g of xy, then the analysis of p being an invariant reduces to g being an invariant, where g is a formula that is equivalent to p in the sense that p is true if and only if g is true for some y. You lost track of the value of y because it's changing, right? But that's okay. In the beginning you had a p, if you have a p, you have a g for some y, okay, I guess that's true in the beginning, right? Y changes in stupid ways, who knows, but at the end g is still true for some y, forgot which one, but that still implies the p. Right? Okay? Example, I think, is a good time. So here's a differential equation and an invariant that we would like to prove. And the invariant corresponds to this green region. And yes, you can try it out. If you start somewhere in the region, you'll stay in the region. But you don't have to rely on pictures. You can also just prove it by saying, form the differential invariant. So prime this thing, which means differential form computations back and forth, that you get 2 omega squared xx prime and 2 yy prime less or equals 0 because c doesn't have a derivative. And then what's more intuitive than replacing the left-hand side of the ODE with the right-hand side of the ODE? Let's do exactly that. The trick is, of course, to prove why that's okay. And then you're left with arithmetic that trivially proves, because if omega and t are non-negative, then because stuff cancels, 2yy squared with a lot of stupid non-negative numbers definitely factors to be a non-negative number. I mean a less or equal 0 number, not positive number. Okay, please keep in mind that it was very important that I had d greater or equal 0 for this, and it came from the evolution domain constraint. Because the next thing I'm going to do is make d change in admittedly completely arbitrary stupid ways, which is the shortest ODE that still fits on the slide. D prime equals 7.
Now d is a variable.
Now d is a variable, right? So in fact, for me, it doesn't matter that much whether something is a parameter or a variable. It's just a variable, and some of them change, others don't change, because that's a notion that's very local to your analysis, right? Even if in the entire system stuff changed, by the time you made it down to one particular sub-question, by decomposing the system, maybe stuff that used to change no longer changes. Or by the differential ghost principle, something that used to not change all of a sudden starts changing. That's why that's not so important for me. But yes, you're right. All of a sudden it is actually a state variable. Okay, yeah, now this proof will fail. Because remember, the proof depended on knowing that d was greater or equal 0. So the most obvious way of proving it is to say, well, I will do, you guess? I will do a differential cut, right? If I can prove that d is greater or equal 0, I'm back in my old proof. Let's do so, right? So first of all, this is now increased damping oscillator, so you kind of see it spiraling in a little bit quicker, but certainly it isn't leaving it, right? If I had this, I would have the old proof. How about I make it so by first asking whether d greater or equal 0 happens to be an invariant for my system, and if it is, I get it up there for free. Okay? So this, of course, can easily be asked. Well, d prime equals 7 I could solve, but okay, never mind. I pretend I can't. And then I will plug in d prime greater or equal 0. We'll find out 7 greater or equal 0, and even I can compute that. And then I can come back with, oh, I get to assume d greater or equal 0 up here, and can do the old proof. Because now I get the d greater or equal 0, which was an evolution domain constraint, so it's part of the description of the system, and I can use it as an assumption from now on. There's one thing that's wrong in this slide. This is an invariant, right? D greater or equal 0. So I get to assume it from now on, but I still need to prove, even if it is inductive, that it was at least true in the beginning. And I didn't say it is. In fact, if we try the system with anti-damping in the beginning, of course, it will not be true that I will always stay in this region if I can. Right? So yes, I also need to squeeze this into the initial condition. I just didn't have space for it. And then the proof actually works. Okay, any question about this proof principle? It's, before I move on. It's very easy, right? You just derive stuff and in the sense of prime, right? And then you derive stuff in the sense of doing a bunch of differential cuts and blah, 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 and then you're done at some point, I hope. The point is, this is very easy to do once you know the invariants. And in particular, the computers are very efficient at checking whether this is right or not. Right? The trick is coming up with them, but once you know them, they're computationally super efficient. And how we come up with them systematically, that's tomorrow's talk. It's not just useful for these little things, it's also useful for more interesting applications. For example, we've tried this on a ground robot, where you've got these collision freedom questions as the ground robot is moving. We've tried these on the European train control system, and on a positive train control system here in the US. We've tried this on the FAA's Airborne collision avoidance system and on the ship cooling system. And somehow feel like I forgot something. Yeah, the surgical robotic system, and maybe some others that I now forgot. So for example, in ground robot collision avoidance, you can try exactly what I said, and find out that the fundamental safety question for ground robot control is the question, when is it safe to do which control action? Obviously, that's always the case, but specifically, when can I accelerate, when do I have to brake, and when do I have to steer? And that's also the same question for self-driving cars. And of course, the answer always depends on what's your safety objective, what are the physical capabilities of your robot, as well as of the obstacles. And the way we did this then is to identify symbolically what the answer is, with prover support in a theorem prover KeYmaera X, and then prove that the system model is then safe. And for example, the answer depends, because if you're passing another car, noticing that you can focus attention to just the cone in front of you depends on the knowledge that the other car is actually stopped and won't all of a sudden start moving over into your lane, for example. Right? But under that circumstance, you can take a different notion of safety, namely this like orientation safety that says, I only need to pay attention to this, and you need to know that the other car won't all of a sudden start moving. When you're approaching an intersection, your notion of safety will depend on knowing where the intersection is and that the intersection doesn't move. If all of a sudden the intersection would move toward you, you would of course have to drive very differently than if the intersection stays put at the point where it currently is. That gives you a bit of a different safety region around it. If you are in the neighborhood of other traffic participants that move, then your safety buffer around you will again increase, and how much it increases depends on you crucially knowing how fast the other traffic participants are. Obviously, if this thing is traveling at the speed of light, even if you have a lot of distance, you will ultimately be hit by it. In particular, what also happens in this case is that you will no longer be able to prove the complete absence of collisions, because it just isn't true. If the other traffic participants around you drive in super crazy, dangerous ways, they could hit you from all sides simultaneously. The only safe thing you could do is disappear, and people haven't found out how to do that yet. Which means your notion of safety being collisions never happen has to change, because it's just not true. Your notion has to change to say collisions never happen while you move. With the idea being that if collisions happen while the other guys were moving, well, they messed up. And that you can indeed prove that collisions never happen while you move. In other words, you are already stopped by the time a collision happens. So if the others drive well as well, no collision will actually happen. But there's another twist on this. And here, for example, if you're approaching an intersection, it wouldn't help you if you would inch into the intersection and then observe that, let's say this is a long and heavy truck, that the other truck hit you. Because this safety notion would say that if a collision happened while I was stopped, that isn't my fault. But that clearly is nonsense by the time we're talking about intersections and so on. In other words, the safety notion needs to change again to what's called passive-friendly safety, which says, first of all, no collisions happen while you move. And second of all, if you stop, you have left enough distance to the other cars so that they could stop and prevent collision. If they then don't, it really ultimately is their fault. You did do everything right. That now depends on knowing the maximum velocity of the other cars, the positions of the other cars, but also the reaction times of the controllers, drivers, or whatever you happen to have on the other cars. So for example, this is a don't throw yourself in front of a train kind of thing, because they can't react very well. So in other words, you have an even bigger region in all of those. It's clear that this is how the picture has to look like. The question is, yeah, great, but what are those regions like? What's their shape? And in particular, after you're done, what's the proof for them? Well, here's all the answers for this. Right, these happen to be the correct answers for all of those, depending on all kinds of parameters, including sensor faults, sensor disturbance, actuator disturbance, and all kinds of things and so on. But the biggest, sensor failures as well. But the biggest question in all of them is, of course, not just why this has happened, not just here's the formula for it, but also how do you find out the formula and how do you justify, if you build a car controller like that or a robot controller like that, that it really is actually okay. And that's where, again, all the proof technology that you saw comes in. Here's a FAA's ACASX system. To give you a bit of a history in that, currently what's flying is called the TCAS, it's a Traffic Collision Alert System, and it's been designed in the 70s and has saved many, many, many lives since. That is helping pilots avoid collisions in mid-air by instructing them to go up or down, basically. And the way this was designed is by a program that was written back when programs were not important yet, is instructing pilots to do something, and every once in a while there was a problem with it, which is why they fixed the program and said, if you're in this particular relative coordinate situation, then please decide differently. And because that sometimes caused problems, they cast yet another if around it. And after a little while, nobody ever really completely understood this thing anymore. So the new design by the FAA is this next generation airborne collision avoidance system, which is designed in a very different way, without the use of programs, because they didn't want to have to worry about programs anymore, and also designed because the current system is reaching its operational limits. And so the way that is designed is in a decision theoretic way, by a gigantic Markov decision process that is discretized on the grid. I told you a little moment ago, model things that are continuous as continuous, not discrete, but of course if you write it down as a Markov decision process, you have to assume a grid-based discrete motion for the system. And then optimize this on a cluster of 1,000 computers for 2 weeks and read off a policy of what the right decisions are. And then at runtime, look up where are you in relative coordinates to the other aircraft, what is your relative velocity, relative relative vertical acceleration, and all kinds of things. And then interpolate the values from the grid to decide what decision your aircraft is going to do. For example, here, this would be the decision to tell the pilot to please climb. But if you're a little bit unlucky, the pilot might have just initiated the descent to go under this one, and so it takes a bit of a reactions time until the pilot does decide, and then will climb until you reach the targeted climb rate, for example. So when the FAA approached us about this verification of it, they correctly identified this as a hybrid system because you've got the differential equations guiding the motion of the true aircraft. You've got the discrete decisions that are happening, and you've got all the different decisions in all the regions of the system. That makes it a hybrid system, but it also does make it a very hybrid system because this is a system with 500 billion different regions. And even though I do like to say that our prover isn't entirely stupid, it's not that good. We can write down a system with 500 billion modes and you loop around it and different equations in it and hope to find a proof in any reasonable amount of time. So the way we did this instead is to symbolically characterize what this region looks like, and then verify that these regions are actually safe if you fly them, and then compare that to the actual decisions in the table to find out whether the real system also works with that. And so the good news is that 97.7% of the 500 billion states that we compared are provably safe or can't be helped anymore in the system design. So that's a lot of success. The problematic news is that the remaining 2% are these 15 billion counterexamples. Here's one of them, for example, where if our aircraft was flying this course and the interior aircraft was flying that course, then some of the circumstances, this one, for example, the ACASX policy that we looked at decided that this aircraft should be issued a do not climb advisory. And the problem is that if the pilot actually does that, so he does not climb, then this will take the two aircraft toward a crash. Whereas had the system kept quiet, then in this particular circumstance, everything would have been fine. And that's of course the kind of help that you don't need. And it so happens that one of the examples we showed them, they also found by half the year of simulation. But with this approach, of course, you find the 15 billion other ones as well. They actually said that's good, but 15 billion is a big number of counterexamples to look at. And so they wanted to find reasons for reducing the number of counterexamples. Because, for example, in many of the counterexamples we reported, the system gave bad advice, but ultimately made up for it again by giving better advice. Things like climb, and later on I said, oh, I meant descend, I'm sorry. Right? And so we dreamed up the more complicated notion of safeability, by which we mean actions that later on you can still make safe. Right? So give some advice right now, which if you follow it for a little while, you can still give good advice later on that saves the day. For example, if you're here, right, then if you give the climb advice for the moment, right, then remember the pilot has a lot of variation in how he does his climbing. It can climb soon and strongly, or late and not so much, for example. And the system can later on still say you need to climb more than you currently do, so which is called strong climb, with a climb rate of 2,500 feet per minute per second. Or the pilot the system could give a reversal and say, I said climb, but I meant descent. And then all of a sudden, the question is, from which other states can you say ahead of time which of the decisions that the system is giving right now is a provably safeable one, in the sense that either it is already safe or you can still ultimately make it safe. And again, we took a look at the system and identified symbolically when that's the case and proved it in KeYmaera X and did the comparison, in which case there were only 900 million examples where it didn't quite work. Here's one of those counterexamples where if the system doesn't give an advice right now, then even 1 second later is already too late, because 1 second later you either the system says, okay, keep on doing what you're currently doing, but then then two aircraft get too close to here, or if the system later on says, oops, I forgot to mention a second ago that you should have climbed with 1,500, by the time the pilot actually gets around to doing that, the two aircraft again are already too close. And the size of these stupid regions is just whatever the FAA works with. I forgot the numbers. 500 feet vertically and 100 feet, 500 feet horizontally and 100 feet vertically, or something. Just below some distance, they either already crashed or there's turbulence that might make them crash and things like that, which is why they're hard trying to avoid this. Although in this case, you could argue it's like borderline, right? So they're not that close at the moment. But whatever notion you fix, now you just run the same verified system again, and you will find out what it should have done. Okay, so for example, if you had like already issued a climb 1,500 feet per minute per second advisory a second ago, everything would have been fine. And sort of this constitutes those 900 million counterexamples. Lots of other systems that we've looked at. How we do this is not just by staring at the system, but systematically in a theory improver, KeYmaera X, where we analyze a model of a system, do a proof. I'll show you in a minute how we roughly do this, and then generate a proof. However, it is also important to realize that that's a proof of the model of a system. It's not a proof of the actual system. And how can you bridge that gap? Well, by writing down a better model of the system. But even a better model of the system is still just exactly that, a model of the system, right? And of course you can say, well, maybe we should take Schrödinger's equations, then you have a quantum mechanical model of the system, but that's still a model of the system, and it's not a very good one to analyze the motion of a car down the road or an aircraft through the air. So the way we overcome this question is by also generating, with a bunch of proofs, a compliance model monitor that is running on the real car or aircraft, whatever, and is observing the real behavior of the system to basically fill in the blanks of the proof at runtime. The majority of the proof we've done offline. The only remaining question is, wait, do the two match? And this proof is then finished online while the system is running. And then overall you have a proof that yes, indeed, this system, as it is currently running, is safe to be used because the model was analyzed for safety and the current run fits the model in a very systematic way, and then everything is fine. It also is a very trustworthy theory improver because it's based on the uniform substitution proof principle, which is originally due to Church, and gives us a sound and complete theory improver with an extremely tiny core of about 1,700 lines of code, but also a lot of automation and interactive user interface and programmability on top of it. In fact, the 1,700 lines of code I want to emphasize because the amount of code that the correctness of the yes proved statement at the end depends on is very minimal in our system, especially if you compare it to our previous generation of the prover, which had 66,000 lines of code that were soundness critical. Now we only have these less than 2,000, so down to 2%. But it also compares very well to other hybrid systems or theory improving tools, which is important in this domain because if people won't find a proof for the system, that's not a disaster. They will try again because they want to verify this thing. So if you have a completeness bug, no biggie, right? But if, unfortunately, the system said, yes, everything is fine, when really it wasn't, then people aren't going to question their proof anymore, because that's the answer they want. They want to be told that everything is fine. And that's why it's important that the core that the soundness depends on is this absolutely ridiculously small 1,700 line of code, which is really just constitutes of literally a copy-pasted version of the accent I showed you, just as text, and a tiny little uniform substitution engine to, expand the concrete formulas into instances. That's all that's happening in these circumstances. Actually, here it is. So uniform substitution is the Church's proof rule. Just we generalized it for this differential in logic, which says that if a formula is valid, then any substitution instance of it is also valid. And the only thing you need to make sure is you pay a little bit of attention while you're doing the substitution, for example, to make sure that you're not substituting free variables into a context in which they're bound very easy. And that's all there is to it. For example, here, this is one of the axioms I've shown you for non-deterministic choice, and the uniform substitution that replaces the red A with this red program and the green B with this hybrid program, and the blue predicate P with this, we'll just rewrite that into this and is also then automatically sound. And that's this implementation plus one copy of each axiom is all we need for soundness regions. Let me show you a little bit how this actually works. So here's the KeYmaera X theory improver. Here's a model. Is the font good enough? Yeah. Okay. Here's a model of a simple bouncing ball, for example, starting in this particular initial condition. So in particular, at height h, which is above the table. And then all behavior of this particular model are such that, well, no results found, I appreciate, are such that we are still above the table but below the initial height. Here's the differential equation for gravity, where you stay above the table all the time. That's what you do when the bouncing ball is bouncing on the table, obviously. The discrete part has a non-deterministic choice. Sorry for funny ASCII notation. On the left-hand side, you start with a test whether you're actually on the table. If so, you invert the velocity by being deflected back up. The average choice is only available if you're not on the table, but then nothing interesting happens. And then the star at the end just means repeat any number of times. And this is actually not meaningful. This just documents the model and informs our prover about what is the invariant that it's going to try during the proof. Speaking of proof, let's start such a proof to give you a bit of a sense of how this works. Here's the original question where we prove an implication by assuming the left-hand side and set out on a journey to prove the right-hand side. Sure thing. What else should we do? Right? As in sequent calculus, right? Assuming a conjunction, of course, is the same as assuming the two conjuncts separately. Sure thing. What else, right? In fact, let me do this a bunch more. Let me unfold all these without actually having to click on all kinds of stupid buttons all the time. Here's the interesting question now, which is how do you prove a property of a loop? Precisely by finding an invariant. And in fact, finding the invariants and doing the proofs from them is the hardest part in the entire enterprise. Here it was annotated in the model. It's very easy. Had I not annotated it in the model, our invariant search procedure would have found it too. In this case, right? But you can write down very big and complicated models where our invariant and generation procedures will go off and never be seen again in their whole lives. But this is also the most important, like, design insight in your system. Like, what do I try to preserve? And then the proof, of course, reduces to showing that in the beginning, the invariant is true. We use quantitative elimination to establish that that's the case. Proving that the loop invariant is strong enough to imply the post-condition we wanted. I will leave that open just for instructive purposes. And the most interesting part is if the loop invariant is true, then after one run of the loop body, is it true again? Which we now split, for example, by semicolon, the axiom we stared at a little while ago. Always after running A and then B, we're safe. If and only if always after running A, it is the case that always after running B, we're safe. So split, in other words, at the arrow, the ODE from the discrete part. Then we can work dangerously in the middle of the logical formula, which usually I wouldn't advise people to do, but because of our uniform substitution, small standard critical core, we can afford to do this without losing correctness. So for example, to show that a system that has a choice is safe, if the left is safe and the right is safe, let's do exactly that. And then here we have a sequential composition again. Let me split the sequential composition. Let me substitute in the assignment. Let me turn the test into an implication, because all ways of running a test were safe. Well, runs only happen if the test condition holds. So I can click that away and click that away. And now all I'm left with is a differential equation. At which point, for example, I can, let's say, solve this differential equation, because we talked about how solving works. This now will actually not just copy-paste the solution of the differential equation into the proof, because then we would have to trust the differential equation solver. We don't want to do that. We want to have minimal number of things on the standard core. So instead, what it is doing is, in the background, conducting a proof, constructing a solution of the differential equation along with its proof, and then plugging that into it. And here you've got the solution, and you can look into prove this by real arithmetic quantifier elimination, which will be done. In fact, what the prover has gathered while I was doing all of this clicking is useful for two reasons: to get an intuition how this thing works, and for me to have a chance to explain what it's even doing, right? There's also the automatic proof button. Don't ever push it, because it'll just prove this thing, and I can't show you anything, right? But what's also useful is this logbook, which is a proof tactic that records exactly what I did, and that you can just stare at to learn how you can program proofs yourself. Because I can also type things down here and say, come on, just unfold this and tell me when you're done. In this particular case, all that we're left with is the loop invariant strong enough to imply the post condition? let me try this proof in a stupid way by hiding the arithmetic from the loop invariant. Let me throw that out. Sometimes this is a great step to help provers when they're stuck by hiding irrelevant facts and try it again. In this case, if I now take out the pocket calculator to prove it, it will come back false. No wonder, because if I threw away the one thing I learned after the loop, I can't be shocked if it's not true anymore. So I take a step back and say, wait, what was that? Is there a counterexample maybe? And it says, yes, there is a counterexample. If you put position to -1, which isn't ruled out, and you say, I guess I get it. Let me take a step back. Maybe I shouldn't have thrown away the loop invariant. Let me try to do the proof now. And it reports back, yes, the result is proved. And in case you want to do that again, here's the tactic that did it. Over time, people are programming the search as opposed to actually doing the search in the way I just did. But everything is exclusively based on, the uniform substitution principle that we've got here, plus the copy of the axioms that I showed you, plus real arithmetic solving. Of course, none of this work would have been possible without the help of all my students and postdocs, and of course the funding agencies and industrial collaborators and so on who supported this. Logical foundations do make a big difference for cyber-physical systems, but also the other way around. Cyber-physical systems also make a big difference for logic because it makes me ask different kinds of questions. For example, the question whether cutting in differential equations makes a difference for proofs. Yes, it does. You can prove that there's things you can only prove if you change with a differential cut the evolution domain constraint of a system. You can also prove that there's some things you can only prove if you increase the dimension of your system with a differential ghost. In fact, that's the thing I will exploit during tomorrow's talks in order to tell you that we can even prove every real arithmetic invariant of a differential equation by blowing up the dimension sufficiently until it becomes so easy that we can do this. So the influence goes both ways. You do have strong analytic foundations and practical roll-up-your-sleeves theorem proving and proof automation things, significant applications, and the opportunity to catalyze many areas of science. But the trick and secret to make it work was this multi-dynamical systems principle, to understand that even if a system is complicated, its pieces are not so bad. If we make sure that our analysis of the whole system is a function of the analysis of the pieces, we've won, because, well, we just decompose it, as you saw in the theorem prover, until the question is, come on, that's just assignment, I can do that. Right? Or until the question is, okay, this is just, a differential equation. Well, after tomorrow, we will be able to do just that. Numerous wonders remain to be discovered. Here's a whole list of all kinds of open questions and so on, for example. But you do see that we actually have really draw in making this happen from many areas of science. Logic, certainly a lot of proof theory, theorem proving goes into this, algorithmic parts, fixed points, stealing from decision procedures. It's something I haven't shown today, but it has a lot of connections to the numerical side as well in terms of error approximation. Stochastic size as well, a lot of differential equations questions. PDEs come up indirectly in our differential games work, for example, or a lot of algebraic things as well, computer algebra, real arithmetic, and real algebraic geometry, and differential algebra, and so on. And then, in fact, there's also, that's not the book I wanted to refer you to, but there's also a textbook that's coming up, hopefully this month. I wanted to, at the latest next month, where I describe the entire thing in a very, very, very accessible way that has a very intuitive read, but gets you exactly to where you need to go in order to fully understand all the details of the reason. And with that, I want to give you opportunities for my questions, and in the differential equations proving hackathon tomorrow.
How do you find invariance?
So yes and no. So finding invariance is proofs. It tells you that if true, there is a proof.
Yes.
Because the only thing you can do with the loop in this is to write down an invariant for it. This proof also tells you that there is an invariant for a loop of a hybrid system, if and only if it's true. It also gives you a constructive recipe to come up with it because it is a constructive proof. Unfortunately, it's also a complicated constructive proof. So I forgot, I think this was something like a 30-page proof or something like that. So it's great that it is constructive, but on the other hand, that's in practice not how you find the invariants. So in reality, our proof automation techniques take 1,000,001 shortcuts in this construction and try and find things a lot more efficiently. And in fact, many of the invariant search procedures that we pursue exploit, for example, fixed point loops in the search, or exploit, for example, so doing something incredibly stupid, which is the following. If you have an ordinary differential equation, if you have an invariant for it, you can prove it, right? That sort of thing, right? Okay, the invariant condition you can characterize as a partial differential equation. If you think about it, the condition is a property that whose derivative is 0 or is equal to 0, right? Okay, that's a PDE. If I can solve this PDE, I know the invariant. So you can reduce the analysis of an ordinary differential equation to instead the analysis of the PDE. Which idiot would do that? The point is, all of a sudden, we can in fact exploit every PDE solver because it is not soundness critical.
Right.
If it lies to us, that's okay. We will just check the answer at the end of the day, and if it was wrong, we'll say, sorry, PDE solver, can you try again, right? So that's one brain-dead stupid way of doing it. That's not so brain-dead, but that's one way we do it. Another thing we do, and partially I'm going to show you this tomorrow, but the proof rules we've seen today, you can staple them together in a particularly clever way, such you define an if and only if. As soon as you have a logical formula that's an if and only if characterization to when it's safe, you can now start generating the things that make it true. So what we can do is write down, for example, in monomial basis to make sure we've got some templates, and then exploit the fact that we've got existential and universal quantifiers in this to say, is there a combination of the parameters that makes the invariant condition true and also make sure it still implies the post condition and is implied by the precondition. Without these two extra, it's stupid because it will always come back with, I found something of the form ax squared plus bx plus c equals 0, that's invariant. It's called a equals 0, b equals 0, c equals 0. And you say, great, wonderful, thank you. That is true but not helpful, right? So it's important to also always have the other ones in there that say, but it needs to be at least true in the beginning, so please don't write down false as an invariant. And it has to imply the thing at the end, so please don't write down true as an invariant, because yeah, sure, but not helpful. Right? So that's, for example, what we do as well. We also have played around with semi-definite programming for generating invariants, but that hasn't worked out so well for us yet. The problem is mostly that with SDP solvers, the answers are essentially always a lie. Of course, they compute with floating points, but it's not just that this particular floating point answer isn't an answer, but nothing really next to it is an answer, and so we have a lot of trouble trying to find actually correct things out of that. In fact, I want to say this in a slightly stronger way. One of my postdocs has looked a lot into barrier certificate generation as well, and he has not yet been able to find a single paper in barrier certificate whose examples were correct. They were all actually incorrect, just floating point errors. And so we haven't, I don't know how to do this yet. So invariant generation for these things is still an extremely hot question, even though we have a lot of techniques for it. But the point is, after tomorrow, what I'll show you is that if we have an invariant, we've got the proofs. That's already very cool. I mean, a little more than I thought was possible, right? But it's still the invariant generation that's like hard. And it's also, of course, also in invariant generation, there's also the complexity question, right? If you have a bunch of invariants, some of them might be an easy one. That's the one you need to find in order to make sure your proof is done and find that short amount of time, right? If this convoluted invariant, right? Great. Of course, in principle, by completeness, we will find the proof, but you can't wait for it. So you need to find a succinct one.
Any questions?
I can ask a bunch of related questions.
Go ahead.
Yeah. So, when you say arithmetic, you mean polynomial arithmetic?
Yeah, so yeah, let me clarify. My differential equations are polynomial differential equations, right? Not really, because if they're rational and you stay away from the singularities, everything actually also still works. Not really, because, for example, if you have sine and cosines or the usual suspects, you axiomatize them away by just introducing new variables for the sines and for the cosines. So we can do a little bit more, but the theory starts whenever you have boiled it down to a polynomial differential equation system. The arithmetic that we then do also is polynomial for the reason that that's when you've got decidability. Of course, rational, sure, whatever, right? But you do not have decidability if you leave sine and cosine functions around by Gödel's theorem. So, in fact, that's also the reason why you can write down very simple differential equations that you can't quite answer. Because x double prime equals minus x has a sine wave as a solution. And the zeros of the sine wave are always isomorphic to the copy of the natural numbers. And Gödel's second incompleteness theorem tells us that whatever we're trying to do, we can't axiomatize the integers.
Okay, so to follow up question.
Yeah.
Maybe then I didn't understand the completeness theorem.
Yes, it is a relative completeness theorem. It says that, it's very subtle. So it says that if a formula, it says that, over here, if a formula is, so, if a formula has a proof, it had better be true, otherwise we're in trouble. Right? That's the Soundness direction. The completeness direction is this way. And that's too good to be true because the logic is too expressive. In fact, you can make a very easy argument why it's violating compactness, so it can't be actually complete. No surprise. You can define Turing machines in there. Right? But the point is, hybrid systems, they've got two hard parts, right? There's the ODE part, and there's the discrete part. Right? Discrete dynamical system, King's dynamical system. Both of them are hard, both of them are undecidable. The point is, however, that even if these look like two independent sources of impossibility, they actually cross-dominate each other. Because if you can just prove properties of differential equations, you can prove every true property about hybrid systems and also about discrete systems, and vice versa too. If you can prove properties about discrete systems, you can prove every true property about ODE. And here, for example, this boils down into like so. A formula is valid if and only if hybrid systems question is true if and only if it follows from elementary questions about differential equations. Now, this is the first completeness theorem. The second one says that, by the way, you could also do discrete systems here. It doesn't matter which one you choose, as long as you choose one. The answer as well. Now, tomorrow's completeness question, so the third completeness theorem tells you, oh, and by the way, these we can answer if it's an ODE invariant question. So an arithmetic invariant of an ODE, we can also prove. And that's precisely now where trouble can still strike us in between. That an invariant exists, but it's not arithmetic. Or we can't find it. But given how challenging the question is, it's quite surprising to me that that's the only way in which disaster can still strike. Oh, the other practical way in which disaster can still strike is that the genius Tarski proved that real arithmetic is decidable, but some idiot later on proved that it's doubly exponential. That's not a good idea, right? So doubly exponential procedures, yeah, I'm not sure if you ask questions with in the quantifier alternation number. So yeah, that's the thing that rescues us a little bit because we're not alternating quantifiers a lot. But still, in practice, that don't expect answer questions with 10,000 dimensional differential equations that are highly nonlinear. It won't work. But because we symbolically decompose, we can, for example, answer roundabout questions about aircraft, about 6 aircraft that completely automatically prove this thing without me providing any invariants or anything like that. It just goes off and does its thing and comes back after a few hours of proof, which is kind of cool.
And so the trust is in the small core you have for KeYmaera and for the quantifier.
And arithmetic. So the two things we need is we have an extremely compelling strong answer for the Soundness core of KeYmaera X, which we also verified in Isabel and in the Koch theorem prover. So the point is that unless they're all mistaken, I think the answer is pretty trustworthy, right? But we still need real arithmetic solving capabilities. And it is possible, we've worked on this, to generate witnesses for differential equation. Nonsense, what am I saying? Witnesses for the real arithmetic by Stengler's real Nullstellensatz. In that case, there's no external trust required at all. We can do everything completely ourselves. But that's still, even if it's theoretically complete, it's not practically complete. Because even if there's an if and only if relationship, a sentence over real arithmetic is true if and only if there is a real English standards witness. Can't find them well enough, right? So in the cases where we can find them, we have a completely rigorous proof from A to Z, and we do that. But in like too many interesting cases, does the search for these witnesses not quite actually work out? So again, it's the curse of dimensionality in disguise, right? If you ask a question, I mean, many of these questions have like 15 variables at least or so, and degree 4, 5, 6. Yeah, existence of witnesses isn't always good enough in practice. But at least there's nothing about differential equations that is in any way that we ever need to trust externally, because it's just a list of axioms like I showed you today. Actually, there will be one extra axiom or so tomorrow, but basically that's it.
Okay, thank you.